All right, everybody, I think I'm gonna go ahead and get started. It's about 10 o'clock, even though the clock on the wall does not say that. I hope that you guys are doing okay today and having a good week so far. Let's see. I'm gonna go ahead, I think, and jump into what I've got on the board up here. Of course, we have some announcements to make as well, but I might wait a few minutes for that. To just kind of get this under our belts first, and then we'll kind of figure out where we're at with everything, due dates on stuff and what's coming up in the next week or so. But before we do that, I thought I might just do a couple of warm-up problems that would close the loop on what we were saying on Tuesday about the power of having a linear transformation in our hands. So I think that's what I'd like to start with here. Notice all I have on my recap up here is just a reminder, basically, that whenever you have a linear transformation, right? If you know that you have something that's linear already, meaning that it respects addition and scalar multiplication, right? Then any linear transformation like that actually has to respect all possible linear combinations. So this is like building up something even bigger, right? So we could take C1 V1 plus C2 V2 plus C3 V3 and so on and transform that. And when we say that T respects linear combinations, what I really mean is that what it says right here, you can pull the constants out, you can split apart the plus signs. And this is really just because T already is supposed to respect addition and scalar multiplication. And linear combinations are just made up of doing addition and scalar multiplication anyway. So that's really not a big surprise. Yeah, so from the definition of what it means for T to be linear, we're not surprised, are we, that T would respect expressions that look like this. These are these so-called linear combinations. So the thing that you can really take advantage of with that, however, is you can get a lot of mileage out of having a linear transformation to do problems like these two warm-up problems. So I thought maybe we could start by taking a look at these, and then we'll get into the rest of the lecture from there. So this first warm-up problem just says, suppose that T has inputs from R2 and outputs from P2 of R. So this is just telling me again what universes the inputs and outputs live in. Okay, so on this problem, I'm plugging in points of R2. This just look like the XY plane. And I'm going to output quadratic polynomials. Okay? And let's suppose that we know that T, maybe we don't have a formula for T yet, but we know for whatever reason, maybe we know already that T is linear. It is linear. Okay, let's assume that it is linear. And for whatever reason, we happen to know that T of 1, 0 is this polynomial right here, 3x squared minus 4x plus 1. And T of 0, 1 is this polynomial right here, which is x squared plus 5. Let's say we know those two values, just those two values. It turns out that because T is linear, we can use those two values to find all of the values of the outputs of the transformation. I can figure out T of any point A comma B. And so that's what I'd like to show you here. And by the way, I did write the extra credit quiz already, and there will be one of the 3 problems on that quiz will be of the nature of what you see up here behind me. So, and it very well could come up on the exam as well. This is a really important kind of problem because it's showcasing the power of having a linear transformation. Okay, and there's also some of them in the homework as well. Okay, so let's see if we can do this. Let's see if we can write down a quick solution here. So the way you want to do this, guys, is if I want to know what T of AB is, what you want to do is try to figure out, well, how can I write AB in terms of the values that I already know? So they already gave us T of 1, 0 and T of 0, 1. So the idea here is to somehow write AB in terms of 1, 0 and 0, 1. We know that we can do that because after all, 1, 0 and 0, 1 is a basis for R2. Right? 1, 0, in fact, it's the standard basis for R2. just these 2 points, 1, 0, and 0, 1. What does that mean? Well, that means that every point AB can be written in terms of 1, 0, and 0, 1. And in case there's any doubt about it, we can just go ahead and do it, right? We can write AB as A times 1, 0 plus B times 0, 1, just like so. So if you just think, if you put the A on the inside and the B on the inside and then add the points together, you're just getting AB back again. And again, the reason that I have done that is because now what I have in these parentheses is really just one of my linear combinations that T must respect, right? T will respect this. So this can be, right, we can use the fact that T is linear to pull out the A, pull out the B, and split up the plus sign. Okay, so this is the idea here. Okay, and then they gave us these values. So they told us what T of 1, 0 is. We can go ahead and plug it in. So we're going to get A times the quantity, 3x squared minus 4x plus 1, and then plus B times the quantity, x squared plus 5. And to be perfectly honest, that would be fine for your final answer here. That would be a formula for T of A comma B. I'm going to go ahead, if you don't mind, and do an optional extra step just to show you how you might sometimes see this written. The optional extra step would just be a little bit of algebra here to kind of put the different powers of x together. So you see we have x squareds in 2 different places. So if I wanted, I could kind of group all of that together and write, 3a plus b times x squared. And then the constant term would be the x term would be minus 4ax. And then the constant term would be a plus 5b. This would be writing the polynomial kind of in a more standard form, right? So something times x squared, something times x, and then constant term. Is everybody following this? So this last step, you could say that this last step is optional, right? It's sort of optional, but I think it's good to write it in a standard form like so. Any questions on that? Does everybody understand it? Audrey.
I'm just about being a basis.
Well, so this is the vector space where the inputs are living, right? So R2. If we think about a basis for R2, of course, there's lots of them. But the best basis, the easiest basis would just be 1, 0, and 0, 1. Those are the standard basis vectors for R2. And because those are a basis for R2, we know that any other point in R2 can be spanned by those basis vectors. And that's really what this first line is expressing. If I take any point AB, I can write it as a combination of the basis. So that's actually a chapter 4 concept. That's not really specific to linear transformations. It's just in general, if you're in the vector space R2 and you take any point A comma B, you'll be able to write it as a linear combination of this basis. Yeah.
I'm sorry,
What you go back and check that it's spanning. So, okay, so really quickly, what's the dimension of R2? 2. How many vectors do I have in this list right here? 2, right? So the K matches the dimension. So these vectors are either both or neither. And I can put them in the columns of a matrix and take the determinant and it won't be 0. So therefore they're both. Yeah, absolutely. In fact, any 2 points that are not scalar multiples of each other would be a basis for R2. So that's reflective of this idea that there can be lots of bases for a vector space. Yeah. Now, other questions on this? This blue writing is what you would need to write down. To be perfectly honest, this one's probably easier than what I would be asking you. Let's try one that's maybe a little harder. I'm going to go to this one over here. This one is a little trickier because, well, you'll see in a second, the given information is not quite as transparent. So let's look at number 2. It's the same idea. It's absolutely the same idea. If I take a transformation from P2 of R going to M2 of R, again, if it's linear, right, guys? If it's linear, then again, I have some given values here. So I told you what T of one is. It's this 2 by 2 matrix right here. I told you what T of 1 plus X is, which is this 2 by 2 matrix right here. And then this third point is 1 plus X plus 2X squared. And T of that is going to be this third matrix right here. Let's assume that we know those values. All of that stuff is given to us. And now the question is going to ask us, okay, based on knowing that, let's try to figure out what T of anything would be. So ax squared plus bx plus c, right? That's a random quadratic polynomial, right? It's just a general form of a quadratic polynomial. And the question is, can we write down, based on these three pieces of information, can we now write down what T would do when it is applied to any other polynomial? So it's the same idea, but in this case, we have slightly different looking vectors because the vector spaces are different, but it's the same idea. It's the same idea. So let's just go through it for the solution here. What do you suppose is going to be my first step? Yes, go ahead, Adrian.
Distribute the.
I can, yeah, basically this is a linear combination. I can just split the T into the separate terms. Exactly right. So this is going to be A times T of X squared plus B times T of X plus C times T of 1. Right, so that's using the fact that T is linear, I can split it up like that. Okay. But now we are going to start to see why this problem is a little harder than the first one. And that's because we need to know T of X squared and T of X and T of 1. But that's not what they gave us. They gave us T of, well, they did give us T of 1. But they did not give us T of X. They gave us T of 1 plus X. And they did not give us T of X squared. They gave us T of 1 plus X plus 2X squared. So the information that we need right now in our solution is not directly given to us like it was over there. Over there, we had the direct information. We were told immediately what T of 1, 0 and T of 0, 1 were. Here, the given information is not lining up exactly with the information that we need. So I think we're going to need to continue this here in a moment, but I'm going to come over here to some scratch work to see if we can discuss how can we get these values that we need in order to proceed with the equation. Yeah, Blake?
Substitute T of 1 and T of 1 plus X.
Okay, if I use these two together, I think that's what you're getting at, right? If I use these two together, I can actually solve for T of X. Does everybody see that? You see, T of X would actually be equal to T of 1 plus X minus T of 1. So just remember that T will respect this expression, right? T of 1 plus X is just T of 1 plus T of X. So if you have T of 1 plus T of X and you subtract T of 1, you'll get T of X, right? So you can actually figure this out. So we put in, we were given T of 1 plus X is -1, 6, -2 and 2. And from that, we now have to subtract 3 and 1 and then 0 and 2. And if we just do this slot by slot subtraction, we'll get -4, 5, -2 and 0. So that's good. We can figure out what T of X is by just subtracting right here. Okay. Now I also have to figure out what T of X squared is. How do you suppose I'll do that one? Go ahead, Alex.
Take the T of 1 plus X plus that.
Okay.
And then subtract the T 1 plus X and divide it by 2.
Nice. I can combine these two together to figure out what T of X squared is. So first I would probably just subtract them, right? So just by subtracting them, I would get T of 2X squared. So let's just figure that part out. That would be T of 1 plus X plus 2X squared minus T of 1 plus X. Again, T respects this subtraction, right? It respects all possible linear combinations. So it certainly would respect that subtraction. Blake?
How did we get T 1 plus X minus T of 1?
So I'm just trying to figure out how I can write x in terms of these two expressions, right? So if you want, you could think of it this way. T of 1 plus x is T of 1 plus T of x. And now if you solve for T of x, it's this minus that. You could just think of it that way. It's probably the easiest way to think of it. But remember, T will respect the subtraction that we have up here on the board. So that should be okay. Okay, so this one was given, right? This T of 1 plus x plus 2x squared, that's 9, 0, -2, -2. And then from that, I'm going to subtract -1, 6, -2, and 2. So I'm just going to do matrix subtraction here. And the result will be 10, -6, 0, and -4. Now that's not T of x squared, that's T of 2x squared. Don't, I threw that 2 in there just to keep everybody on their toes a little bit. So if I know what T of 2x squared is, then as you know, this 2 could pop out in front, and then you could divide it into the entries of the matrix, yeah? So I'll just come over here to write the final conclusion. T of x squared would just be 1/2 of this matrix, 10, -6, 0, and -4. And let's just divide everything through by 2. It'll be a little nicer. 5, -3, 0, and -2. Okay, so that is what we would have for T of x squared. So I now have T of 1 was given. I solved out what T of x was right here. And I solved out what T of x squared was right here. So now I can go back and plug everything in. Yes.
I'm sorry, can you re-explain the 2 of x squared? I was a little lost on that.
So remember that T respects scalar multiplication. So you can pull, so this is equal to 2 times T of x squared. You can pull that 2 in or out of that input to the transformation because T will respect scalar. So we know that we can pull constants out. We know we can split apart plus signs. We can actually totally bust apart an entire linear combination. Is that a little better?
Yeah.
Yeah, so I'm just pulling the 2 out, and then when I want to solve for T of x squared, I just have to divide by 2. So throw the 2 as a fraction onto the other side of the equation. It's looking okay. So in this case, this would be A times the matrix 5, -3, 0, -2. And then it would be plus B times T of x. T of x was -4, 5. And then the second row is -2 and 0. And then finally, we have plus C times T of 1. T of 1 was actually given to us originally. We can just recopy that matrix in right there, and that would be an answer. That'd be a good answer. Just like I did over here, I kind of cleaned up the expression a little bit. I can do that here as well, because what you can do, guys, and we will actually want to do this, be able to do this, so not a bad idea to practice it now, which is to just combine all of this into one matrix. So if you just kind of focus on the upper left corner of the matrix, for example, you see you have a 5A right here, right? And then to that, you're going to subtract 4B. I'm just looking at the upper left corner, and then add 3C. So this would be compressing all of the terms in the upper left corner like so. I can do that for all 4 corners of this matrix. So the upper right corner would be -3A plus 5B plus C. Okay, and then in the lower left corner, I would have -2B. And in the lower right corner, I would have -2A plus 2C. Notice there are some zeros in the bottom row, which makes the second line look a little bit easier. And so this would be your answer. So now if I asked you, what is T of 9x squared plus 8x plus 7? Or any other polynomial, if I took any quadratic polynomial with A, B, and C values, so I can pick my favorite numbers, 9x squared plus 8x plus 7, you would just need to put in 9 for A, 8 for B, and 7 for C, and write down the the entries of this 2x2 matrix. That would be the answer. That would be the answer. What do you think? Does this make sense? Pretty good? Okay. I do want to point out something. Oh, here's a question for you. With the t of x squared that I just erased it. I'm really good at doing that. Erase exactly what you need. It's okay. With the t of x squared, would it have been okay to say, oh, that's just x times x, so I'm gonna split that apart as t of x times t of x. Since I already know what t of x is, I could just do that. Would that have been okay? Definitely not. We never said that t respects regular multiplication, right? T will respect addition and scalar multiplication. It will not respect, this is a regular multiplication. This is not a scalar and a vector. This is like two vectors. Okay, so please be careful here, guys. T is a very nice function, but we can't take this too far. So I'm only bringing this up because I've seen people do this. Otherwise, I wouldn't have known about it. Okay, good deal. So there is going to be another one like that on the take home quiz. Yeah, by the way, before I go any further, just a quick let me make a couple of quick announcements now that I think everybody's here. The homework that is due from section 6.1, this is number 14. Originally I said it was going to be due tonight. I decided, well, there's no reason it has to be tonight. I'll give you till tomorrow to do that one. I just want you to get it in pretty early so that you can start studying for the exam. After this homework, there's no more homework listed, and there won't be until after you're done with the test. I am going to have extra office hours tomorrow, actually, because we're kind of getting close to the test now. I normally on Fridays, I don't have extra hours, but I have to be on campus anyway in the afternoon to do something. So I'll probably hang around a little bit longer than that. I think I'll show you the updated midterm review packet in just a little while. Anyway, we should have no trouble getting this done because guess what we're going to do next in class today? We're going to go through a lot of these problems. Okay, so I will help you with the homework and we'll just use it as practice. Okay, so it should be an easy assignment. Everybody should nail it pretty much if I am able to do most of those problems. So then the only other thing that is kind of going to be on the radar, I have not posted it yet, but as you know, for each exam, because my students last semester complained that I don't give enough quizzes, still can't get over that. I decided, okay, I will give a quiz, but this will be an extra credit quiz that you can take home. This will be, there's only 3 problems and each problem is worth 1 point towards your next midterm. So you can get up to 3 more points. Some of you have already, most of you have already gotten points for watching that video a week ago. So this one will be due on Saturday though. So you'll have basically an extra day for this. I'll post it up. I'll try to post it up as soon as I go down to my office. I wrote it last night and I would recommend definitely doing it. I mean, it will take a little bit of effort. These are 3 problems, but they're all going to involve some work. But the thing with the quiz, I will post the solutions to the quiz after Saturday night. And I will not help with the quiz, however. Okay, so this is the quiz, it's extra credit. So I'm happy to talk to you about it starting on Sunday if you don't understand everything from the quiz, but try to do it without my help. I would also suggest that, or I would not just suggest, I would ask that this doesn't just get thrown up on a discussion board. So if you're working on the quiz with somebody, I don't really mind that as long as you're learning something, but please don't just post it up so that like somebody who doesn't have a clue what's going on is just going to copy it. That's not helpful for them and it really isn't helpful for anybody really. So I don't mind you if you want to work together. Try to not work with anybody who's outside of this class. Don't ask my SI leader for help. Don't ask your engineering professor for help. Try to do this as best as you can on your own. Okay, so as long as I feel like things are being done with good academic integrity, I'll continue to offer this extra credit quiz for each exam this semester. So anyway, that'll be due on Saturday. And then other than that, we have our midterm, as you know, on Tuesday. So that's on Tuesday, and I will show you the review packet one more time in Canvas. There's 2 sample midterms. There's a review session that has some video with it that you can watch if you're interested. You don't have to, of course, it's just totally optional. And then there's a review packet. This kind of has a summary. Here's all the things you should be able to do for this exam. Here's a list of the important terminology that you should know, and stuff like that. Okay. I think relatively speaking, there's less stuff to memorize in this part of the course. It's more procedural things. It's not like equations that you have to apply so much. So I hope that at least with respect to that, it'll be a little bit easier. I will give you the Gram-Schmidt formulas though. So that's something that's a little technical. I'll give those to you on the front of the exam. You'll see it on the sample test. Okay, but I don't even think I'm gonna need to give you a table of integrals for this one. It's just not, this isn't really, this material is not so much dependent on that. If I end up writing a question where there's an integral, I'll just throw the table there. So, okay, any questions? Not so far? Okay. What I'd like to do next, guys, is work on the homework with you for a bit. So we have quite a bit of time today to review. I also have 2 group works that we're gonna do because I'm behind on doing group works, but we're gonna do some of the homework. So far, only one problem made it up onto my board. I assume there might be others. So I'll start with 28, and then in the meantime, you know, be thinking about if you want to ask me about any of the other ones. 28 is a good one for us to look at. Definitely is a good idea. So let's look at 28 from this is for the homework number 14 that's due tomorrow night. Hopefully we can pretty much get it done today, actually. So on 28, we have a transformation T that goes from R4 to R2. And we are given T of 1, 0, 0, 0. This is equal to 3, -2. And then we are also given T of 1, 1, 0, 0. And that value was 5 and 1. And then they gave us T of 1, 1, 1, 0. And this was equal to -1 and 0. And then we have T of 1, 1, 1, 1. And that was given as 2 and 2. So this is all given information, right? Again, guys, don't worry if you haven't done the homework yet. I know you just turned in one like 2 days ago, so that's okay. We're just gonna work these out together. And the question is, find the matrix of T. This is a good chance for me to remind you that whenever you have a linear transformation from Rn to Rm, remember from Tuesday, we can always represent that transformation using a matrix, and we actually call it a matrix transformation. Do you guys remember what the size of this matrix would be? I'm going to call it capital A. In this case, do you know what size the matrix would be? 2 by 4. Everybody's got that down. Perfect. 2 by 4. Let me get myself set up with enough room to put that here. Yeah, it's going to be a 2 by 4 matrix for sure. And then let's see if we can remember how to fill in the matrix now. I wrote down kind of a generic formula for doing that. You might remember that what the formula was is that you basically want to transform all of the standard basis vectors. In this case, there would be 4 standard basis vectors for R4. So my input vector space is R4. That's why there's 4 columns. And so this was do you guys remember this? This is the notation for the matrix of that linear transformation. And so I can see right away that the first standard basis vector is 1, 0, 0, 0. And so the values 3 and -2 should go into the first column. Okay, so that much is easy to do. But where we run into trouble here, guys, is that the second column is supposed to be T of the second standard basis vector. So just to remind everybody, E1 is just 1, 0, 0, 0. E2 is 0, 1, 0, 0. Now they didn't give that to us. They did not tell us what T of 0, 1, 0, 0 is. So what do you suppose we're gonna do? Jerry?
You can multiply E1 by -1 and add it with E2. Or the second T, where is this 1, 1, 0, 0?
This one?
Yeah, to get E2.
Yeah, so how do I get E2 from the information here? I don't think I want to use a -1 multiplication. Marco? Subtracting, right? So let's just subtract. Take the second one minus the first one. It's actually the same thing we did right here. It's the same thing we did right here. Okay, except this time we don't have polynomials. If we take the second one minus the first one, maybe over here on the scratch side, I'll write down what T of 0, 1, 0, 0 is. It's literally going to be 5, 1 minus 3 and -2. Okay, so it's literally this one minus this one. Does everybody see that? If you take the second vector minus this first vector, you'll get 0, 1, 0, 0 on the left side. And so if I subtract that, I just get 2 and 3. Slot by slot subtraction, I just get 2 and 3. And those are the numbers that go into the second column of this matrix, 2 and 3. Okay? With me?
E1 and E2 are like the standard.
Those are just the this is E2. E3 would be, 0, 0, 1, 0, and E4 would be 0, 0, 0, 1. I used this notation a week and a half ago or so when I was talking about bases for Rn. And this is just standard basis vectors where you have a 1 in the ith slot and zeros everywhere else. Yeah. Okay. Everybody else good so far? The next column should be T of E3. So I need to know T of 0, 0, 1, 0. Did they give that to us? No, they did not. So how am I going to get it? Subtract the second one from the third one, right? If I take the third line minus the second line, I'll get exactly 0, 0, 1, 0 on the left. T is respecting all of this subtraction. So I will just simply get -1, 0 minus 5 and 1. And if I subtract that out, I'll get -6 and -1. And so that goes on the third column, -6 and -1. Okay, and then finally, we need to figure out T of 0, 0, 0, 1. One more time, they did not give us that value, but can we create that value from what is given? Gilbert, what do you think?
-1, 0 minus, or, yeah. No,
Which of these are you looking at?
The last two.
The last two, right? I notice, right? If I subtract, okay, so 1, 1, 1, 1 minus 1, 1, 1, 0 leaves me with exactly this 0, 0, 0, 1. So I'm going to do subtraction. It's actually going to be 2, 2, right? Minus -1, 0. I think that should be okay. That's what you were getting to. Great. And so if we actually calculate that one, it looks like it's going to be 3 and 2. And so that would go right here. Okay, and so that would then be your answer. That would be the matrix for this linear transformation. So anytime you have a transformation from Rn to Rm, like we do here, you should be thinking in terms of, oh, there's a matrix behind the scenes, right? I'd like to write down that matrix if I can. Good enough? Okay. While we're on the topic of kind of this using the power of linear transformations, why don't we do a couple more of these homework problems that are towards the end of the assignment? I think I might do both of them, 31 and 33. I think 31 is actually pretty straightforward. Come back over here. We're just going to do more of the homework together. That just gives you guys more time to study for the exam. try to help you get your homework done today. So let's look at number 31. And what it says is, well, let's take T. T is gonna go from P2 of R to P2 of R. And on 31, it says that it's linear. So assuming it's already linear, then what it's asking is if they give us that T of 1 is X plus 1, and they give us that T of X is X squared minus 1, and then they give us that T of X squared is 3X plus 2, right? Then the question is asking us to find T of AX squared plus BX plus C. This is the number 31. So here's what I'm gonna do, guys. I'm gonna give you 2 minutes to try to do this yourself. 2 minutes. Go ahead on your paper there. This is the homework for tomorrow night. Let's see if you can work it out. What is T of AX squared plus BX plus C? Yeah,
Okay, I don't know.
yeah, go ahead.
Why don't you start with T of the two,
Uh-huh.
over here, let's just have a T of the two.
Why did I start with that? Well, I didn't really start with that. I really started with T of E1. But see, T of E1 was given. This is
okay.
E1, so I could just straight away, I didn't have to calculate anything there, I could just put it right into the matrix. So this is T of E1, this is T of E2, this is T of E3, and this is T of E4. This one was given. Yeah, the other three we had to calculate. Yeah. One more minute, guys. Let's see if we can figure out T of AX squared plus BX plus C. And then we're gonna check out what you guys have come up with. Yeah. If you get that one done, you can look at 33, because we're gonna do 33 next, which is the next problem. I'll write it down while I'm giving you guys a little more time. Okay, let's take a look at 31 and see if we can finish this one off now. So I want to know what T of AX squared plus BX plus C is. Does anybody want to try out their answer with me? Alex.
Like work through the whole problem.
Just give me what you got for an answer.
We'll go forward like A and then
Uh-huh. Times
3X plus 2
times 3x plus 2, good.
plus B. X
Okay.
squared minus 1
X squared minus 1, and then
C X plus 2.
nice. Did anybody simplify that one? Marco?
BX squared plus CA plus CX
3a plus c?
Yeah.
Yeah, times x, okay, good.
plus 2A minus B.
2a minus b plus c. That look good? That's it. That's all you gotta do. That's number 31. Okay, so that's the answer to that problem. Again, this one is kind of nice because the given values are the T of 1, the T of X, and the T of X squared. If we go to number 33, which is actually also from your homework, it's a very similar kind of problem, but this time the given information is not quite as user friendly here. Not quite as user friendly, so maybe this one we can talk about it together, how we would go. I mean, we still, the philosophy here is still the same. I wanna bust this apart using the fact that T will respect this linear combination. So I can still, start off the same way. I can write it as A times T of X squared plus B times T of X plus C times T of 1. Okay, same thing we've already done like 4 or 5 times today. But this time, see, they didn't tell us what T of X squared is. And they didn't tell us what T of X is, and they didn't not tell us what T of 1 is. So we have to figure those things out from what's given here. Okay, so this time we have to work a little bit harder with this. Does anybody have a suggestion, kind of where I could start, working on the information here that they gave us? Is there a good place to start anyway? Marco, do you have an idea?
The second one, you can divide both sides by 2.
Yeah, the second one is actually the easiest of the 3 to work with because there's no adding or subtracting. It's just a scalar multiplication here, so I could pull the 2 out of the T of 2x and just pull the 2 in front. And if I do that, then I can solve for T of x by dividing by 2. So T of x would be 2x, right? So because 2 times T of x, right, we're just setting this one equal to 4x. Those 2 boxes are equal. Then I just divide through by 2, I can solve for T of x. Okay, so we know what T of x is. Where can we go? So that's gonna ultimately go right here. This will be T of 2x, T of x will be just 2x. But I still have to figure out T of 1 and T of x squared. So kind of looking at what we have up there, do we have any idea where we could maybe go next to get somewhere with this? Jerry?
Are you able to multiply tx by 3 and then subtract it from t3x plus 2 and then divide it by 2 after?
Okay, yeah, we could say, look, this is what T of x is. I noticed from this third equation that I have a 3x. So it might be helpful if we figured out, like here, we could say, this would tell us that T of 3x would be 3 times 2x, which is 6x. So we would know that. And what Jerry is suggesting, which I think is a good idea, is that we can now subtract, right? If we take the T of 3x plus 2 and we subtract the T of 3x, that will tell me what T of 2 is, right? So let's actually do that. Again, I'm kind of doing some scratch work over here. If I take T of 3x plus 2 minus T of 3x, this is just, on the one hand, it is just T of 2 by the fact that T respects subtraction there. That is just T of 2. But what is it as a expression in terms of the outputs that we have? T of 3x plus 2 was given as 2x plus 6. And T of 3x, we just worked it out, it was 6x from directly above here. And so now if you clean this up a little bit, which we should do, 2x plus 6 minus 6x is actually just 6 minus 4x. So if we simplify that, that's going to be T of 2, 6 minus 4x. You guys all following that? So then if that's what T of 2 is, then what is T of 1 going to be? 3 minus 2x. You cut this in half, right? Just cut it in half. So 3 minus 2x, which we can put right there. 3 minus 2x. Okay, so I'll write that one down. That's T of 1. And we're only missing one part now, which is I don't know what T of x squared is yet. Can we figure that one out pretty easily though? How can I, what part of the information do I want to use for that? Blake? Yeah, I'm going to use the T of 1 and the top one, right? The x squared minus 1. So exactly, I can figure out T of x squared. Let's just do it right here, guys. T of x squared would just be T of x squared minus 1 plus T of 1. T respects addition. So we could just literally write it like so. And I know what t of x squared minus 1 is. It was given as x squared plus x minus 3. We now know that t of 1 is 3 minus 2x. I can use that information. And if I just add all of that together, I'm just going to get x squared minus x. And so that is what would be going in for t of x squared. Something like that. Okay, and so this is great. If we want, we can clean this up again, right? So let me just actually write it out. A times the quantity x squared minus x plus b times 2x plus c times the quantity 3 minus 2x. And let's do the same thing we did on the previous problem where we get the x squared terms together, the x terms together, and the constant terms together. In this case, I see the only x squared is right here at the front. So that's ax squared. Okay, but then if I look at where are the x parts, there's a x right here that has a minus on it with a. So negative a for that one. And then there's an x in the middle with a 2b in front of it. And then there's an x at the end with a minus 2c. So all of that, I'll factor that x out of everything that has x with it. And last but not least, I have a constant term. What's my constant term here?
3C.
Just 3c, right? Just 3c. So that would be an answer right there. That's a good answer. Does that look okay? All right, I'm getting lots of practice with this the power of linear transformations here. So those problems, 28, 31, and 33, those are the last three problems on the assignment for tomorrow. So there's a handful of others though as well that I could also work on, maybe of a slightly different nature. Are there any questions though before we go on? Let's just see what time it is. Losing track of time because I don't have a good. Okay, yeah, we're fine for now. Okay, let's go on. I'm gonna go back to the beginning part of this homework assignment, and I want to do the very first problem on the homework for tomorrow, which is number 3. And again, if you haven't done this yet, I don't blame you. I know that we just did the previous assignment a day or so ago, so we'll just do this together, right? Basically doing the homework together and just consider it as practice. So on number 3, we're going to take t to go from C2 of I to C0 of I. Let me just tell everybody before I go any further. This notation, I don't think I've been very explicit. I have certainly not used it very much. This is some interval I on the x-axis, right? The real x-axis. And we're talking about calculus functions here. So this is that vector space of calculus functions. And so you're going to plug in a function. The 2 that you see up here is referring to the fact that these aren't just any old calculus functions, but they are only the calculus functions that you can take 2 derivatives of. So this has something to do with how differentiable the function is in the classic calculus sense. And you'll see when I write down the formula on number 3, why we need to have 2 derivatives of these inputs to the transformation. Because basically they're going to give us t of y. So we're going to plug in a function and we're going to call the function y. And the function is going to spit out y double prime plus a1 times y prime plus a2 times y. And so now you see that, okay, in order to even make sense of this transformation, right? In order to even make sense of this transformation, I have to be able to take 2 derivatives of whatever I plugged in. So it's important that the inputs are twice differentiable. And that's what this C2 of I means. don't worry too much about it. It's not gonna play a central role in what you guys have to do for this section, but just to be very precise, that's the way it would look. Okay, now what this problem is asking us to do is to show that t is linear. So now we are not assuming that it's linear, we are showing that t is linear. And what do we have to do to show that a transformation is linear? Okay, t has to respect the addition and the scalar multiplication. Exactly, so that's two parts, right? So t respects addition, let's write that one down first. See how this one would look, t has to respect addition. So what that means is that if I start with t of, let's say, y plus z. Okay, I'll just use another similar letter. Remember, the y and the z are functions here, right? You have to always understand the context of the notation. These inputs are calculus functions. So it's y of x and z of x, for example. Okay. So how does this work? Well, again, over on the left side, we're always going to just write only white space over here. I don't want to see people writing on both the left and the right side, because that gets disorganized in a hurry. So let's just try to write it only on the right side here, okay? And so how's it going to look? Well, whatever we are plugging in to t, we have to take two derivatives of it first. So that would be y plus z with a double prime on it. And then adding to that, we have a1 times, again, the first derivative of whatever we plugged in. Well, what we plugged in right now was y plus z. So we have the first derivative of that. And then lastly, we have one more term here, which is a2 times whatever we plugged in. Whatever we plugged in. In this case, that was y plus z. Okay. So we are verifying that this is a linear transformation, that it respects addition, right? That's the idea here. So what's my next move going to be? Johnson? The derivative?
Yeah.
Yeah, basically the derivative can be broken up, right? You guys know this from calculus. If you want to take, if you have, e to the x plus sine of x, and you want to take the derivative of it, I'm sure you all know that, well, you just take the derivative of this one plus the derivative of that one, right? So that's just a property of derivatives, and we're going to use that kind of here just in abstract form. So y double prime plus z double prime plus a1 times the quantity y prime plus z prime, and then plus a2 times the quantity y plus z. Okay, so yeah, that's how that might look. And what would you want me to do next? I could distribute those A's. Let me do that in conjunction with something else. Grouping them is the key thing here. How do I want to group them? All the Y's together in the front, all the Z's together in the back. Remember, guys, if you forget or if you get stuck and you're like, this is too messy, I don't know what I'm doing, you can always jump to the end, right? You know what you're supposed to end up with. At the very bottom, we should have t of y plus t of z. If I see that, it might help remind me that I need to have all of the y parts up in the front and all of the z parts in the back. So this is just one more step in between here where we're going to exactly do that. So we'll get y double prime plus a1 times y prime plus a2 times y. So Audrey, I'm distributing the a's at the same time that I'm grouping the y's together. And I'm going to do the same thing with the z terms here. So z double prime plus a1 z prime plus a2 z. There we go. And yeah, that's exactly what t of y plus t of z should look like. Just put a little check there. That verifies that step. Okay. T respects addition. Okay, what else do I need to check? That t should also respect scalar multiplication. So I think I have enough room over here. T should respect scalar multiplication. So how that's going to look is I'm gonna start with T of K times Y on the left side. K times Y, so start with that, and then what I have to do is my goal ultimately is to get the K factored out, but I'm not gonna start by doing that. I'm gonna leave my white space here on the left side, and I'm just gonna do a bunch of steps now. Okay, so I have to take this K times Y and plug it into this function. Everywhere I see a Y, now I'm gonna write KY. So this will be KY double prime plus A1 times KY prime plus A2 times KY. Everywhere I see a Y, now I have put KY. Awesome. And where would you have me go from there? We know from calculus that constants can always be just pulled out of derivatives, yeah? So I can just take this K out in front, K times, whoops, sorry. This would be K times Y double prime plus K times A1 times Y prime plus K times A2 times Y. Yeah. And next. Johnson? Factor out the K, exactly, there's a K in every single term. Let's just factor it out, that's the algebra step here. Y double prime plus A1Y prime plus A2Y, awesome, and that is K times T of Y. Put a check on that one too. Yeah, Jordan? Oh, so this, just think of this as this input can be anything you want. So I've expressed it using a Y notation, but if I wanted to know what T of Z is, everywhere I have a Y, I just think of it as a Z now on both sides. And it could be any letter that you chose, actually, that same principle applies. Yeah, for sure. This is a nice example because it shows that taking the derivative is linear. Of course, you already knew that. In calculus, you learn that when you take the derivative of a sum, you can split it apart. Or if you have a scalar, you can factor it out. Do you guys realize that if that was not true, if this was not linear, we wouldn't be sitting here. This class wouldn't exist. There would be no differential equations in linear algebra. You're like, darn. Now I have to go through a whole semester of math just because of that. Right, because if taking the derivative was not linear, if it didn't respect the linearity properties, then we wouldn't really be able to use linear algebra to help us with differential equations. This is actually the whole reason we study these topics together, is because linear algebra is a tool that is very helpful for studying differential equations. And if this had not been true, if taking derivatives was not linear, then those two subjects would suddenly be on icebergs floating in opposite directions. There would be no parallels between them there. Yeah, Marco.
Just remind me, so when we do the zero vector check, if it doesn't, if it's not valid, then multiplication and addition. What if in this case, multiplication and addition does apply, does the zero vector automatically have to be valid?
Yes, so you're bringing up a good point. I did not do the zero vector check here, which I probably should have. The zero vector check would just be making sure that if you plug in 0 as your function, this is not the number 0, by the way, this is the function 0. If you plug that into your formula, that means take 2 derivatives of 0 plus a1 times 1 derivative of 0 plus a2 times 0. You just need to make sure that you do get 0. If that had failed, then we could have stopped and said, no, it's not linear. But it passes the zero vector check. And so then we proceed to these 2 steps. And you are right. If we only do these 2 steps, then and they both work like they did, then that zero vector check must have worked as well. Yeah, good point. Okay, great. See, in this case, the question was asking us to verify that T was linear. So this wasn't a yes, no question. It wasn't saying, is T linear? It says, show that T is linear. That's why I didn't do the zero vector check, because I already know that I'm supposed to be showing that this does work. So I might as well just get right to the heart of the matter, which is that T should respect addition and scalar multiplication. Yeah, good question. That's a really good point. You guys want to do some more of these? Keep it rolling. Okay, we'll go another 5-10 minutes, then we'll take a little break. We're gonna have most of this assignment done. Let's do number 6, which is the next one on the assignment, I think. Number 6 has a transformation from, well, C0 of AB. So it's kind of that same notation again. This is the vector space of calculus functions. And we're mapping this to R. And the formula is T of, and then we plug in F here on number 6, it's T of F. That's a function. And the way we're going to spit out an answer is we're going to do an integral. Okay, so it makes sense if we just did the derivative example that we would follow that up with the integral example. And again, so we're going to integrate f of x from a to b. And this one is going to tell us or ask us to show that t is linear. Same instructions again, show that t is linear. So the idea here, guys, is again, since we're showing that it's linear already, I gotta get my camera over here. Yeah, since we're showing that t is linear, I don't need to do the zero vector check, although you easily could. Let's just start showing that t will respect addition and scalar multiplication. So t respects addition. So again, how that might look is, okay, we're going to do t of 2 vectors added together. I might use f and g. Try to use notations that are compatible with the type of vectors we have. Like on a problem like this, I wouldn't want to see something like this. If you write t of a plus b, I'm thinking, oh, there's a matrix, right? These look like matrices. Well, no, this problem does not have anything to do with matrices, so it's better to not use matrix letters if the problem doesn't involve matrices. So let's use f and g here. If you use y and c again, like we did over there, that would be fine. Okay, but just something that looks like a function. Okay, first step is to add these two things together, but it's already added together because it's abstract enough that you really can't simplify that expression. So we can just go straight to the formula. So this is just going to be the integral from a to b of f plus g of x dx. Just literally put f plus g in there. And yeah, what am I going to do with that? Johnson?
You can distribute
Sorry?
the integral.
Distribute this integral. Before I actually do anything with the integral, let me just explain what f plus g of x is. As a function, f plus g of x is just f of x plus g of x. It's like literally that is what it means to add two functions together. So I would probably do that first. And now I think this is what you were talking about. We can pull this integral apart, right? We know this from calculus as well. This is just the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Just make it into two separate integrals, right? Pull them apart like that. And now you see that you're basically getting what you want, which is the first part is t of f, and the second part is t of g. The formatting is really important here. Make sure that you're not writing on the left side of these, and make sure you're putting nice equal signs to connect these steps, right? If any of this stuff is missing, then it's not as clear what you're actually trying to do. So the write-up should be written as cleanly and clearly as you can possibly do it. Okay, let's see. Oh, we also have to do the scalar multiplication. Can I just do that pretty quickly? Don't think this is too hard. With integrals, you guys know this, right? You can pull constants out. Do it all the time, right? So that's basically what's gonna happen here. T respects scalar multiplication. So this time I'm gonna start with T of, let's say, K times F. So K is my scalar again, like I always try to use. And the goal here is to get that K out in front, but we have to derive that. We can't just, again, people do sometimes get in trouble here because they want to pull the K out right away. That the K should not come out until you actually get to the end. Then the K will be on the outside. The first thing we need to do is just plug straight into our formula again. So this would be the integral from A to B of KF of X dx. Okay. And what can I do from here? Now I can pull the K out. Exactly. K is just a constant inside the integral. So what we know is that integrals will allow constants to be factored out. So I can put the K on the outside of that integral. Makes good sense to me. And now what I have is the K on the outside multiplied by T of F. And again, that's what we want. So pretty predictable, no real surprises there. It works out pretty nicely. Questions here? Awesome. Well, let's do another one. Let's go to number 12. So I'm gonna crank this out. It's gonna be a free homework assignment, almost free. I want to give you as much time as possible to study for the test. That's why I'm doing it. Otherwise, I'd make you guys do all this work. So on number 12, we're gonna go T from R2 to R2. The formula here is gonna be T of X1 comma X2 equals X1 plus X2 comma 2. And the question on this one is T linear? Is T linear? Anybody got the answer? Jerry?
It's not linear.
It's not. I agree with that. Let's give everybody 15 seconds to think about how Jerry knew that so quickly without even having to like write anything. We know it. Let's see. Blake, why don't you, I wanted to give people a moment to stare at it. Why can you tell me immediately it's not linear?
It doesn't.
Okay, that would be true, but a faster reason. Johnson?
The zero check doesn't count.
Correct. I would just do the zero vector check.
That's what I meant.
That's what you meant. Perfect. Yeah, if you just check it, right, T of 0, 0. Right, you plug in 0 everywhere, what do you get? Well, you get 0, 2. That's not the zero vector. Okay, so this fails. So the zero vector check fails and we're done. Let's say that you just, hit your head on a rock right before the exam and you forgot the zero vector check when you came in here. Please don't do that, by the way. If that were to happen, you could just check that it doesn't respect addition, because what would happen is if you took two vectors here and added them together, you'd get a 2 plus 2, and 2 plus 2 does not equal 2. That will ultimately be why this thing is not going to respect addition. So it is true, but this is faster and easier. This is the faster and easier way to do it. Any questions on that one? Let's keep rolling. We only have a few more to go. 15, yeah, Gilbert, go ahead. Yeah, if you wanted to do it. Yeah, you could, well, first of all, if you think it's going to pass, keep in mind, this is Rn to Rm. Anytime you have a transformation from Rn to Rm, you can try to represent it as a matrix transformation by just simply writing down the matrix. And then do we all remember that we were witnesses on Tuesday that Dr. Annan showed forevermore that matrix transformations respect addition and scalar multiplication. We wouldn't really need to do it. If you wanted to though, Gilbert, just for you, I could write you a special exam. You know, we could actually create 2 points here, and then we would have to add them together inside the parentheses like this. Right, to make a single point, then we could actually plug this point into the formula, so it would look like, you know, whatever is in the first slot plus whatever is in the second slot, right, comma 2. And then the question would be, could you break this apart? And you're not going to be able to break it apart as something comma 2 plus something comma 2. That's where it's not going to work. Okay, so if you really did want to get down in the technical verification of it, it might look something like that. Yeah, Marco?
Just to clarify, when you did prove the vector transformations are always linear,
Yes.
that's only in the case of an M and.
Rn to Rm. Correct.
So the case of an N or MM, where they're both equal.
Oh, they can be equal. Yeah, there's no problem here. If they're equal, that's still true. Yeah, is that what you're asking?
Yeah.
Yeah, they can be the same number.
Okay, but they had to.
No, definitely don't have to be different. They usually will be different, but they don't have to be, and we could use that idea.
Okay.
Yeah, so if it's a matrix transformation, then we can just state that. But see, this, just because, okay, guys, very careful here. Just because this says Rn and Rm doesn't mean that it's automatically a matrix transformation unless you can actually write down the matrix. This one's not going to have a matrix. If there was a matrix here, we would have answered yes. We would have said, yes, it is linear. So in this case, there is no way of writing down a matrix for this formula. And it would be a 2x2 matrix if it was possible, right? And you could say, well, I'm going to plug in my x1, x2 here. I can do a 1 and a 1 right there to get, you know, x1 plus x2. But the problem is the second slot. I mean, I can put, see, if this was a 0, then we could have just put 0 and 0 here and it would have worked great. But if I'm supposed to get a 2 over here, right, then I don't see how to do that by putting numbers on the second row here, because this is like an x1 times something and an x2 times something. It's supposed to always equal 2. This is just not going to be possible to set that up. But that's kind of the idea there. Good point. I'm glad that you guys are asking good questions about that. That's definitely a good point. Actually, the rest of the problems that we haven't done yet for the homework are all about these matrix transformations. Let me just show you. I'm just going to maybe do, I am going to leave probably a couple of these for you to do, just to practice. But 15, it just says find the matrix of T. And on 15, the T, by the way, goes from Rn to Rm. And on 15, they give you the formula T of x1 comma x2 equals x1 plus 3x2 comma 2x1 minus 7x2 comma x1. And so they just want you to figure out the matrix of this transformation. So you can assume that this is a matrix transformation. And we just have to, all you have to do, and guys, you don't even have to show any work, is to write down the answer. What would be the size of this matrix? It's M by N. What are the M and the N here, though? M is, well, sorry, let's start with N. 2, right? That's because there's, so you actually have to count the slots. There's 2 slots here, so N is 2. And then how many slots on the output that corresponds with M? 3, right? So there's M is 3, N is 2, so the size of this matrix will be 3 by 2. M by N, always, 3 by 2. Okay, And what I have to do now is put the numbers in. I have to put the numbers in. So how do I do that? First row is 1, 3. Second row is 2 and -7, and the third row is 1 and 0. That's it. That's it. That's number 15. I'll let you guys do 17. Let me just do 20, and then I think I'm gonna be letting you do the last two on your own. I'll do number 20, and then we will have almost done everything. This one, they give you the matrix. So 2, -1, 5. And 3, 1, -2. They give you the matrix and they ask you to determine T. So the question is asking you to determine T. In other words, they want you to find the formula for T. By the way, in this example, T will go from what to what? Yeah, it's a 2 by 3 matrix. It's a 2 by 3 matrix, so remember, we're always switching the M and the N. So this one would be from R3 to R2, right? That's actually the opposite of the one we just did a minute ago. Okay, now that's the inputs and the outputs, but I actually want the formula. When it says determine the transformation, they just want us to write down, well, what would be T of X, Y, Z? Or if you want, you can call it ABC. Any letters here is fine, but they just want the formula. You think you can get it? You don't have to show any work here either. This is just reversing the process of the last example. The last example, we started with the formula, we wrote down the matrix. Here, we're starting with the matrix, we're gonna write down the formula. You think you can do it? What you have to remember to be able to do it is you just have to remember how the matrix transformation actually works. From Tuesday, right? T of X is equal to A times X. So here's A, and I have to multiply that by my input vector. So if I'm going to input X, Y, Z, I always would represent it as a column. So I can represent that as a column. And if I now just do matrix multiplication, I'll get the answer. So what's the first output going to be? 2x minus y plus 5z. Excellent. Then we put a comma. And how about the second output? 3x plus y and minus 2z. That's it. And you don't have to say anything else. It's not asking you to do anything other than just write down the formula. Pretty sweet. Guys, I think I only left you 2 problems to do for tomorrow night. You should probably do them for tonight. I don't know why I extended the homework. You guys can pretty much turn that in like just a few minutes. Let's take a break. It's about 11:20 or so. Let's take a break. And then after the break, I want to do more reviewing for the midterm. I'm going to pass out some group work and let you look at a few more problems. Well, let's take 10 minutes. But this is not a vector space of R4, right? This is working with P3 of R. So when you're busting out the A, which I think is what you're doing, that's great. But you're not leaving behind a 1, you're leaving behind an x cubed.
And then plus X.
And then x squared, and yeah, exactly.
So what's that?
So just the way it's being, you're doing the right process, but the way the vectors look should not have slots there. So. So every space, that's, what you need to do is list out the variables. And the first variable that I see is So what I wanna do is don't this thing is, where do I see the, right there. Yes, so I don't think that's right.
Dimension is.
Then here's another example. This time, square root is plus squared. Here I have no, here I have an n with a minus 3 in it. Okay? I go like that, and then I go to the next variable and do the same thing. So that's how you start the process. Right, right. When they ask you to find a basis, the basis should just be a set that has a list of the vectors. So that's the first one. Comma, separated. This is now. And so.
Oh, yeah.
Now, if you put it as this exact.
Well, we
Then yes, lay them in the. And ultimately put these things into the matrix, but you wouldn't do that from the start, right? The start is sort of the busting out of the polynomial. Okay. I'll let you say, I'll work on that. I'll let you down.
Mark was on the summer. That's good start.
You just check it later.
Yeah, that works great, and so your basis is just, yeah.
So this one, we need to create a form. That's just getting. Yeah.
And you're actually also, base, they also have. I don't, exactly, but, test that, these are things, the allowance of the.
Yeah.
And,
That's why I had them like this.
yeah, exactly. That's about it. But right now, I say, yeah, I need to make sure we're listing out the variable. Yeah.
And you target them has been.
Started, make sure everybody. We're looking at all the page pairs, don't have. Where's this coming from? Ask this. He'll be over there. Okay, hey, that looks good there, Thomas. If you guys don't wanna bust everything out there, I'm okay with that. Just gonna get the idea how it works. But you have it set up. Yeah, exactly. If you can just start it off and you know how it works, I'll be good with that. That looks good now. That's the dimension of P3 of R. What's the dimension of S? So actually, right.
I have. And then the dimensions.
So take those out.
Yeah, but.
Yeah, it's, it should not be. It's busted with very. So I was. That's fine. I remember what's the dimension of this? Oh, no, just A. How'd you get that? Yeah, there's eight different letters, so those are the. Excellent. I am happy with this. Okay, that's great. Anybody need help? Jason? How we doing?
Yeah.
Yes.
Oh, because then you multiply threes.
All of these are. There's like your faces. This guy. This. And you laid those in these columns, right? But I think what the problem is that there should naturally be a filter. So x cubed plus x squared minus 3 should have been written down for this. Cause there's a lot through and this one, right, so it's just, this one would have a 0 here and then a 3. So the size of the matrix was just a little.
Also, the note.
Now we can hear. Zero that would be. Oh, I is gonna be doing zero. It is. Yes, it is. The hashtag is for spanning sets. And these things are spanning sets. So if you do the ERS, which you don't use, you'll find out that things are LI, and so this is your base. Yes, yes, that's right. So there's the
Oh,
first
that.
When you're writing this down, don't write down the A, the B, the C, just list the actual.
And A and then it's like 1 0 0.
Right. Write down the form of the vectors, bust out the variables. If we would get like A, this is that. So
I barely remember. I don't remember.
Is it? So.
I don't think it's about eight. It's fun. It's fun. Don't worry. Oh, they cancel that. Oh, yeah. What?
Wow.
I'm just gonna leave them at terrible subjects. Like, find my two. You can still say.
So, something happened, I don't know what that. Because one of three difference. Yeah. We're gonna go extension, or they could wait.
Yeah. Yeah. So if we just have 2, 3, 4. Because both those, both of it was.
Yeah.
Space.
It's one there.
So the null space.
Yeah.
Would have 3, 3 variables. Okay. Group 9, let me say W equals. And then we would.
Yeah.
So then we would have. We would basically have.
If all the.
Would you like
Yeah.
I know.
Those that are determined that you're like more than normal, then affect this. Was it 8? Yeah, that's right. So we actually did like. It's.
Because these were actually from your home. And.
Eight to zero.
From Pittsburgh nine. I would highly recommend that.
Anybody need a hand? Jardo? Yeah, what's up? Yes, please.
It's the same part. It's not exactly. This one, the question was all the rows and columns. This is slightly different. The.
Not guaranteed.
Entities of the matrix. Combined, that would add up to zero. There's nothing about the rows or the columns, it's just all 9 entries. The big thing is gonna be, what is the resurrected form? Because it's not quite. There, it's the same height.
This is a lot of. So much to remember.
Row space, H.
For sure on the bench. But.
Okay, no, is that all 9 of these numbers have.
I'm sure.
So what I'm gonna suggest is that
That's so.
you want this last slot, this very, very last slot. That's the slot. Another example, the last entry was canceling out everything else. Because. Solve for I and the others, yes, you could do mathematically, you could do it one way that way. Exactly right. That looks good. How'd you guys do? Next up, why don't you skip to problem 2? Let's go to problem 2 with the 5 minutes you have left. I think that would be a reasonable one. You guys doing well? Looks good, looks good, looks good. Oh. Glad you're working on those. Yeah, we. Yeah, you're great. Doing the house. Yeah. You're gonna use that. Yeah. That's so good.
Oh, yeah. It is a lot.
Yeah, because that's a lot. It is. All that has to be soon. No. It's great.
The first one.
Rush down. What kind of, what does it tell you? I suppose, yeah, I know. Yeah, we suggest. Yeah. With a lot of time. These are mistakes. Because the next whole list. Wrap that one. That's correct. That's really good. And I was saying dot, 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 yeah. You don't need to write it out. Yeah. I don't. And you're only having a couple minutes, so I may not get it all the way done, but there's still how you can. And then of course the solution. I thought you said we're gonna like. On this one. Oh, okay. But you gotta like. Zero. So. Right. But other than that, right, like zero, that's gonna be zero, that's gonna be zero.
Yeah, so oh, it's supposed to. I thought that's about.
Oh, I didn't talk about.
And this, times this, times this. Yeah, so
First thing I think I'm getting the union will be doing something.
yeah, I realized. I didn't know that.
I don't want it either. I just, my life's not really nice.
Even though I still haven't done my separate.
Oh, so yeah, all of this week, maybe. I think in fact, these are three.
Hey, guys, can I get everybody's attention here? Because we're pretty much right at the end of the time we have now. If you want to stick around an extra minute and just check anything with me, I'm happy to do that. Don't forget that the solutions to these group works are in Canvas. So if your group didn't quite finish all of these problems, I would highly recommend in the next 5 days before our exam, take a few minutes to go over these group works again. Also, I have a lot of office hours between now and next Tuesday. If you need help with anything as you're studying for the exam, I hope that you'll come see me or shoot me an email. I want you to do well on Tuesday, so study hard and yeah, do your very best. I'll be around to give you a hand with that. Tomorrow I will be doing them, let's see, I have to give a talk from 1 to 2, so it's gonna be after that. I put it in the handout. Let me send an email out about, I think it's like from 3 to 6. Okay. I'm going to dinner with a friend, so I'll be out in the evening for a little while, but I think in the afternoon I should be okay. For sure.
Thank you. You're welcome, guys. Thank you. Thank you so much.